So I'm going to talk about how climate models work. Are they good enough for what we need them for, and could they be better? It couldn't be more extreme. Maths is so applied. First of all, I'm going to tell you why do we need climate models, because as an applied mathematician, we don't do anything unless somebody needs it straight away. Government policy is based on climate change predictions. For example, they regulate energy costs, and they just regulate where to build power stations, how many power stations. They set emission regulations. They decide on when and how many new reservoirs to build, where to build flood defences. And all of these policies are based on climate change. And so you cannot make any of these policies without a climate model to make predictions in order to make decisions about all these ways that we spend money. So I'm going to describe in a very basic terms how climate models work. Are they good enough to answer all these questions that we're asking of them, and could they do better? So I'm going to first describe in a very fundamental way what a climate model is. The climate models, the dynamical core, the very heart of a climate model, solves the fundamental equations of motion in the atmosphere and ocean. These are very accurate equations. They're old-fashioned Newtonian physics, but for predicting the weather and climate, they are very accurate. So the temperature, for example, one of the things a climate model predicts is temperature. This is calculated by solving the heat equation, I've made some assumptions to tell you the heat equation to make it look simpler, but this is mostly what the heat equation is. We start off by writing dt by dt. So capital T is the temperature and lowercase t is the time. So dt by dt is how the temperature is changing with time. The temperature the changes in the temperature are going to be governed by the winds. And I've got up here, I've got my three directions, x, y, and z. And in those three directions, the wind is called u, and it's called v, and it's called w. And for example, if it's cold over here, and it's warm over here, and the wind is blowing this way, and I'm here, it's going to get colder because the wind is blowing the cold air towards me. So that is described in the heat equation. The rate of change of temperature is equal to u dt by dx minus u dt by dx minus v dt by dy minus w dt by dz. And so what this means is if you've got a wind u like this, and you've got a temperature gradient, it's cold here and it's warm here, you multiply those together, it's going to get colder. So dt by dt is negative. And that's the same for the v direction and the w direction. There are other things that make it hotter or colder in one particular location. There is heat from the sun, makes it warmer. So that's heat from solar radiation. Heat from infrared radiation. For example, the ground can warm up, and then it'll radiate heat to the atmosphere. And that'll make it heat up. Latent heat of evaporation. When water evaporates, it leads to cooling of the atmosphere. And then when water condenses again, it forms water droplets in clouds. It produces heat. And then there's also radiative cooling to space. On a clear night, it'll get very cold because lots of heat will radiate to space. And so all of those, you can calculate the magnitude of all of those, multiplied by 1 divided by the rho is the density, and Cp is the heat capacity. And those tell you how the temperature is changing. And then finally, there's the work done against gravity. So I told you before that W is the wind going upwards, G is gravity, and Cp is the heat capacity. So this is telling us that if air rises, so it has a W, and we've got some gravity, then as it rises, it has to cool because it's doing work against gravity. In order to solve this equation, we need U, V, and W, the winds, and we need to know all these other things. We need to know density. And with our very, very similar equations to this, for each of these components of the wind and the pressure and the humidity and all various kinds of pollutants. So all these equations are solved to each of the components. And these are extremely accurate representations of the real world. They're not they are Newtonian physics, but they're more accurate than we could ever want. However, the problem is we can't solve them exactly. This differential equation just doesn't have any useful solutions. especially as there are many of them. There are differential equations for the winds and density as well. So weather and climate forecasting models, what the dynamical core, the heart of the forecast model is, they solve these equations approximately, which is a huge field of mathematics and meteorology. So how do they solve them approximately? This is the crucial part that so many applied mathematicians work on. The atmosphere, the simplest way of describing it is that the atmosphere is split up into a very large number of grid boxes. So a grid box over all of space, and then throughout the depth of the atmosphere there are grid boxes. And each of those grid boxes has just one value of wind, pressure, temperature, humidity, and each type of pollutant, which is clearly not accurate because the wind, if one grid box is, say, 100 kilometres, the wind is not constant throughout that grid box, but these kind of approximations have to be made. And so we need to solve this heat equation for temperature. We need to find out how temperature is changing, but we've only got these values on the grid boxes. So how are we going to solve an approximate form of this heat equation? If we can calculate all these terms, then we will know how the temperature is changing. And so if we know the temperature at the initial time, that's an important part, we need to know the temperature at the initial time, we can then calculate the temperature at a subsequent time. So the most obvious way of doing this, the simplest way of doing this, is if you say, I want to know my temperature T here in this grid box. And so I need to calculate dt by dt, I need to calculate dt by dx, and dt by dy, and dt by dz. So if I calculate here, I'm assuming I know the wind, because that's calculated by another part of the climate model. So I need an approximation for dt by dx. And so approximation, if I'm here, dt by dx is approximately going to be t to the west minus t to the east divided by the distance between them. So that's, in this case, that distance between them is d. So that's t west minus t east divided by 2d. That d is the distance between them. And I do the same for dt by dy. It's t north minus t south divided by the distance between them. And the same for dt by dz. And then I'd also do the same thing for dt by dt. But I don't know. I know what the temperature is now, and I want to know what it is at the next time step. So if that next time step is a time delta t away, then I say that dt by dt is approximately equal to the t new, what I want to predict, minus t old, what I already know, divided by delta t. So now I've made it. There are the other terms which I won't describe. These ones are the most difficult to predict and model. So now that I've got approximations for all these, I'm going to substitute them into that equation and rearrange it. And lo and behold, I can rearrange it to find out what T new is, which is what I want to calculate. I want to calculate new temperature where I am as a function of everything at the previous time step. So there it is. I've substituted all of those into there, and I've got temperature at the new time step as a function of all the other things at the old time step. And when it comes to the calculations, I'm going to explain it in more detail. This is the equation that, as in groups, you are going to solve. Fry Richardson was a famous meteorologist who dreamed of he did solve these equations, but he didn't have computers. So he solved them by hand. And he could only do he could only make very short forecasts on very coarse grids, and his forecasts were not very useful. But he dreamed of creating a huge forecasting factory in this huge spherical room full of people, and each person is doing the calculations from one grid box, and they're telling the person to their east what the temperature is and telling the person to their west, and the person to the west tells them what the temperature is so they can work out the temperature at the new time step. And he has this great big pointer. If somebody's going too slowly, he points this at them to say, you're going too slowly. And I've got this. So I want to try to solve this equation in the same way that Fry Richardson dreamed of. However, I'm not completely crazy. Rather than getting you all to work on the same forecast, which would be very difficult to organise, you're going to be divided up into 4x4 grids, so groups of 16 people. And each person will represent one of these locations. And you will be told the temperature. On your sheet, you are told the temperature at the start time. And then you have to, on your sheets, that you are reminded of the temperature, the equation to predict the temperature at the next time. So you're going to predict the temperature at the next time from your initial conditions. And I'm assuming that there's another part of the climate model that's calculating the winds. And so the winds are already known. I've got a cyclonic circulation like this, which very often happens over the UK. So that's going to stay fixed throughout the calculation. And now I'm going to, first of all, we're going to try to, I'm going to fill in the top line of this in order to help you, show you how it's done. But before I do that, I need my fabulous helpers, which, who are now standing up. Could you stand up? These fabulous helpers are going to be assigned to either one or two groups, depending on how many groups there are. So the first thing, before I describe how to do the experiment, I'm hoping that you're going to assist the helpers and move around so that if you don't want to do the experiment, sit somewhere where there's no piece of paper. And if you're willing to help, join a group with a spare piece of paper so that the helpers will help to arrange you into those groups. And then I'm going to describe how to do it. Could you find another empty group that's not full and get people to move around? What's happened to this row? Okay, we're going to make a start on this experiment. So, quiet now. We're going to make a start on this experiment. I'm going to show you how to do it. I'm London, clearly, and I'm going to try to predict the temperature based on my surroundings. So I know, I'm told at the top, my initial temperature for London is 23. So my first T old is 23. I also have got the time step, delta T, and the distance between space points, D. And our prediction is going to be once every hour, that's 3,600 seconds, and the distance between the points is 100,000 metres. So if I calculate that, it's 0.01, and then divide by 2. So I can put in here 3600 divided by 100,000. But I haven't got a calculator, and you don't need a calculator either, because we're going to do this approximately. And so I'm going to say, well, that's exactly 0.018, but I can't do sums that accurately, so I'm going to say that this is, the sums that I can do is this is 2 divided by 100. And this number, the time step, divided by 2 times the space step, is going to stay the same throughout. So I can put that in throughout. Rather than this, I'm going to have 2 divided by 100. So I can multiply by 2, divide by 100, and here 2 divided by 100. And so you can do that without talking to your neighbours. You can put that calculation in. The other thing that I know is going to stay the same throughout is I know the wind where I am. I am London, and I have decided that the wind is at the top is U is 6 and V is 2. If you're a different location from London, then you're going to have different winds, and they're going to be written at the top. So whatever your U is, you put that in here throughout, 6. But yours will be different unless you're London. And then my V is 2, so I'll put in that 2, 2, 2. Now, the next things I need, in order to calculate T at the new time step from T at the old time step, I need the temperature to my west, east, north, and south. So I need to ask my neighbours. That's why it was so important that you're sitting in a grid and you know who is to your west and east and who is to your north and south. So I am London. I've got numbers here for the initial conditions, but not for the other conditions. So I can do it all by myself for the first time step, but for subsequent time steps, you have to talk to your neighbours. No talking to your neighbours yet. That'll come when I say so. No talking to your neighbours yet. You're doing this by yourself for the first time. While I'm doing this by myself, and then you'll do it. So I know that T to my west, I'm London, is Bristol, and that's also 23, so I put 23 here. To my east is Southend, that's 23, so I put 23 there. To my north is Peterborough, that's 21. To my south, I haven't got anybody to my south, so I'm telling you all boundary conditions, the temperature outside this domain. So this is like a local weather forecast. T to my south is always going to be 25. And if you're on a boundary, if you're at the edge, you are told at the top here your boundary conditions. And you can also see it from this grid, so I'm going to put in 25 here. And all of these sums you can do without a calculator. So I'll do 23 minus 2 over 100 times 6 times 23 minus 23, that's 0. Plus 2 times 21 minus 25 is minus 4. So that whole thing is minus 8. So I've got minus 8 here, multiplied by 2, divided by 100. That gives me 16 is 2 times 8, and then I divide by 100, move the decimal plate, 0.16. So I've got 23 minus 0.16. So my new temperature is 23.16. And now I've predicted the temperature for 1 hour. So I put this new, so now I want to predict the temperature for the next hour. So I put this T new to here T old. So that's 23.16. And for the next time step, I need the person to my west, east, north, and south to have calculated their temperature as well, which I haven't got neighbours. So I can't ask them. But you will then ask your neighbours what is their temperature that's here and here to put into here for you and calculate the new time step. Not yet, not yet, not yet. Yet. No. OK, so now I would like you to predict the temperature in your grid for the first time step and for the second time step, with help from your helpers if necessary.
I think so, yeah. So that would be 16 over 100, which is 425.
You've done it. Oh, yes, you've done those bits. You've got your first time step. Have you told your neighbour what you've got? Have you done your first time step? Fantastic. So now you need to tell your Humber. So you need to tell your neighbours who are not sitting in the right places.
And then you need to take that away from me. Yeah.
How's it going? Making sense? Fantastic. You need to lay that bit next. I have some more data for you. I think most people have now done 2 time steps. So I want you to stop talking and listen for a moment. A lot of people have now done 2 time step and something has happened. There were more terms in the equations than on your sheet. There were also the terms describing inputs of heat, like from sunshine and rainfall and things like that. So some things have happened after the second time step. I don't need to be so close. The sun has come out in the south, of course. So I want, if you are Swansea, Bristol or Southend, after time step 2, where it says T extra, I want you to add 2 degrees to your temperature. And because London has an urban heat island, because it's such a big city, I want you to add 5 degrees to the temperature if you are London. And there is another term in the equation, so there's a gravity work term. When air rises over mountains, it cools. So if you are Snowdon, the air is now rising over the mountain, so I want you to subtract 4 to your temperature. And then following that, share those new temperatures with your neighbours and calculate the temperature for the third and final time step. Does that make sense? Go for it. Fantastic. I forgot to say, only 1 decimal place.
Well, they're all doing however many they feel like.
Yes. Fantastic. Great. Well done. How's it going? Got there. Fantastic. Well done.
We're going to 4 decimal places. So we get a good
I should have said it a bit at the beginning. Don't worry about round-off error. Some people now have finished, so we're going to stop this experiment here because there's more material I want to cover. So quiet now. I've got the answers are on the board. Quiet, everyone. So a lot of you have finished. So we're going to, some of you have finished. The answers are now on the board. So these are the temperatures after the first time step, after the second time step, and after the third time step. So hopefully at the end you've got numbers that look something like this. They won't be exactly like this. There are a few reasons they won't be exactly like this. Some people made mistakes, and then when you make mistakes, the errors that you make will move around. You'll propagate. Other people will feel them. People use different numbers of decimal places, and all the numbers will be slightly different, and those chain errors will propagate. But hopefully the numbers you have are something close to this. And we can visualize what that looks like. So this is the temperature at the beginning, cold in the north and warm in the south. And it changes over the time steps like this. So as you would expect to happen, where you've got northerly winds and it's cold in the north and warm in the south, it gets colder in the south. And vice versa in the east, if you've got southerly winds, it'll warm up in the east. And then I also added those heat islands. And the temperature's rising over the mountains, it gets cold there. It warms up in the south because the sun's come out and there's an urban heat island over London. That's what you end up with. And these equations are solved in similar ways, but not exactly the same, for the entire grid of the world in order to predict weather and climate. There are many other things that come into climate models. And how it's calculated. There's the solar and infrared radiation, which is in vertical columns. So in a climate model, the sun doesn't shine diagonally and heat up diagonally. It only heats up one column of grid boxes. And then the Earth radiates heat back to space. And so this solar radiation heats up all of the layers, then heats up the ground most of all, and then the ground radiates heat back to space and back to the air above. If there are clouds, we all know that the thing that makes it cool is if there are clouds. So what happens if there are clouds? A lot of the solar radiation is reflected back to space, and then the climate predicts the clouds and doesn't heat up the surface so much because it calculates that this solar radiation is reflected back to space. However, the clouds are warm, and so they radiate heat back down to Earth, which we're familiar with. If it's a cloudy night, it doesn't cool down so much because the clouds are warm and keep us warm. They radiate heat back to the ground. So, but how do climate models predict clouds? Because clouds can be tiny and very complicated. And I was talking of grid boxes of 100 kilometres apart. And clouds are often much smaller than this. So how on earth can a climate model hope to predict the temperature if it can't predict these tiny little clouds with tiny little features over mountains? And clouds can also be in very, very thin layers, like this stratocumulus, which we often see during high pressure, which just keeps it very dull and cool. And then big thunderstorms. And this is a typical grid box size, and you can see that a lot of the clouds are a lot smaller. The answer, and this is where climate models lose a lot of accuracy, and there's a lot of work to be done, is parameterizations. So they're a lot less mathematical and a lot less accurate for predicting processes that are smaller than the grid size. We can't solve the fundamental equations if all the fundamental equations are saying is everything is constant in this grid box. So in order to make predictions on those scales, we just have statistical relationships that say something like if one grid box is lighter than the grid box above, then the air will rise and clouds will form. So it can't see that those clouds, it doesn't care what the size of the clouds are. It just say, yep, there'll be clouds in this layer, which does lead to some inaccuracies. There are many other processes that are predicted in climate models. Well, volcanoes aren't predicted, but their influences are predicted. They cool the climate for a few years. There are pollutants that affect the climate. Things like snow and river runoff are predicted in climate models. The river runoff is based on how much rain there is. There is evaporation of water from the surface, which forms clouds. Many processes which help to make the climate model more accurate, but are not always predicted very accurately. So can we trust climate models? I've just been talking about where the errors come in. This is the results from the most recent Intergovernmental Panel on Climate Change Fourth Assessment Report. And these orange lines represent the temperature predicted, a global average temperature predicted from 14 climate models over the past century. So you know when over the past century we know when some volcanoes are, so we can put those in, and that we know how much they cool the climate. The red line is the average of all those climate models. The black line is the observed temperature over the 20th century, and none of the climate models are doing exactly what the black line does, and they never will, because as Lorentz, the famous meteorologist who described chaos theory, predicted, these predictions are chaotic. You can predict the average of what will happen, but you can't predict exactly where it's going to go. So these climate models are predicting that, on average, the temperature was stayed about the same over the first half of the 20th century and then rose. But the exact day-to-day variations are just not predictable. And they are following approximately what the observations do of a global temperature. However, if you run those same models and you don't have greenhouse gases increasing over the 20th century, you just run it and you keep the greenhouse gases constant, then all the climate models are now in blue and they don't warm up over the second half of the 20th century. And now you cannot say that any of these are a realistic model of what this is doing. So this is a fundamental argument to say that global warming is due to humans releasing greenhouse gases. You've still got the cooling due to the volcanoes, and the second half of the 20th century just doesn't warm up. None of these models, the black line goes really close to the edge of all the orange lines in the top there. It was warmer in the 1940s than any of the models predicts. And this argument has been used by climate skeptics to say, sometimes the climate just does warm up like this, and your models are just too rubbish to be able to predict it. And there's been a huge amount of research on this. And this is an area in which I'm not an expert, but actually, if you look at this, it's not outside what all the models are doing. It could have been chance that there were some volcanoes that were not accurately measured. Measurements are not always accurate. There were a number of large El Niños which warm the climate, which these models are not simulating because they're simulating El Niños in their own time. But there are probably going to be more answers as to why this happened. There are already a number of answers. People are probably going to do more research and find why there was the 1940s warm period. So can we trust them? I've showed you the global mean temperature. That's not a lot of use if the government wants to say, do we need more reservoirs in this country? So climate models also predict, this is the precipitation. This is the observed precipitation, the annual mean over the whole climate. And so you can see it's very wet along the equator, and in other bands along, for example, the storm tracks right up there is very... Storm track coming towards us is this band of precipitation here. So we would also like climate models to reproduce that precipitation pattern. So if it can, then if the precipitation patterns change, then we can have some faith that those are realistic changes and we should do something, make more reservoirs or flood defences, or even, heaven forbid, stop producing so much carbon dioxide. So the annual mean precipitation from 14 climate models. It has a lot of the features the same. It's got the strong precipitation along the equator and other bands, storm tracks like in the North Pacific and the North Atlantic. But you can look, if you look closer, you can see that you can spot a lot of differences. And so really, I mean, in particular, this is so different from up there. If this predicts a change in this storm track, it's very hard if it, say, shifts slightly north or south, and therefore the UK will be significantly drier or wetter. It's so inaccurate anyway that it would be hard for us to say, is the UK going to be wetter or drier? So the IPCC fourth assessment report found some robust findings. This is what they're certain of from the accuracy of the climate models that we've got. The warming of the climate system is unequivocal. That was one of the headline messages. Most of the global average warming over the past 50 years is very likely, they had a definition of very likely, due to anthropogenic greenhouse gas increases, human greenhouse gas increases such as carbon dioxide. And then if we continue to pump out so many greenhouse gases, the warming will get even faster. That's what they're certain of. So they're certain enough to say we really should try not to produce so many greenhouse gases. They also said there are a number of findings that are really quite uncertain because they can see that the models are not accurate enough. Any predictions, any regional predictions of drought, changes in tropical cyclones, changes in extreme temperatures, heat waves and cold nights, and the frequency intensity of precipitation, they are very uncertain. So really the government is not in a position to say, there's no problem with climate change, we'll just build more reservoirs. We don't know that that's what's needed. We might be flooded. They say anything smaller than continental scale is unreliable. And this is due to the cloud feedbacks. The models of clouds are not accurate enough. We don't know how much heat is taken up by the ocean and how much is taken up by the land. And then there are carbon cycle feedbacks. So if it gets warmer, trees grow faster and they trap more carbon. But at some point, when it gets warmer, the trees will die. So then a lot of carbon from the trees will come out into the atmosphere. And these are very uncertain. We need to be able to predict these and can't. So we do need better climate models. How on earth can we get better climate models? The most obvious answer is we need higher resolution. We don't need to decrease the size of those grid boxes so we really can predict clouds. And the largest computer in the world, in June, I think, I assume it still is the K computer in Japan, which has got 500,000 processing cores. So it's like 500,000 of you, but if each of one of you is a fantastic supercomputer. And so you divide up the planet across this half a huge computer and get it all to calculate a small region and communicate with its neighbours. So each sub-region is on a different processor of a supercomputer. Because they all need to communicate with each other, this is actually a different computer. The Earth simulator was the largest computer in the world a good few years ago now. And this is a photograph taken of all the cables underneath the floor. Because of all these great big, each of these cabinets is about this high and this wide. They all need to communicate with each other to work out, to tell each other the temperature and all the other fields in their location. So there's a huge amount of communication goes on. And eventually, what slows down climate models is this communication can't keep up. Probably what slowed you down the most was making sure you're communicating with the right person and communicating the right information and just saying the number to each other. So how can, faced with this communication not being able to keep up, how can we improve climate models? Most climate models use a latitude-longitude grid like this. The Earth is split up into latitude-longitude grid boxes, which can be very accurate. It's a very good way of doing things in many ways. However, all the grid boxes get very, very close together. And the weather in this location, if I'm sitting here near the pole, or anywhere, the weather right here is influenced by the weather in the sort of a region a few hundred, 1,000 kilometres around me. So in order to predict the weather here, over a few time steps, I'm going to be communicating with all the grid boxes within a few thousand kilometres of me. If you're right up here, where the resolution is very high, much higher than down here, there's going to be a lot more communication needed to communicate the weather just a few hundred kilometres. So this is a communication bottleneck. So at the moment, I'm working on a project with the Met Office looking at alternative grids of the atmosphere, such as this is a cube divided up into squares, which is then blown up into a sphere. And if you do this, there are errors come in here because your grid boxes are no longer square, they're all distorted, and that can produce errors. There's also a hexagonal icosahedron, which is mostly hexagons, and 12 pentagons, which I think this is going to be the way forward. So some new climate models in the States are being built with using a hexagonal icosahedron. But there are problems. It's not clearly the best solution. And the best climate models still all use a lat long grid, but it can't continue. Another option that I have done some work on in the past, but not so recently, is to use a non-uniform grid. So, for example, if this is the precipitation on 1st of April 2010, and if you divided up if at every time step you divide up the sphere differently, you could put a lot more grid boxes where there's something happening, and then have a more accurate forecast only where you need it. But this is not a technique that is gaining any popularity at the moment. It's unlikely to become operational within the next short time, however long that is. So conclusions. Climate models are accurate enough to know that human activity is warming the climate. So they are accurate enough to inform policy for governments to set targets to reduce emissions. However, they're not accurate enough to predict regional climate. And another generation of mathematicians and scientists are needed to create the next generation of climate models that will be able to make these regional predictions. Thank you very much.
It seems intuitively quite interesting and sensible to look at the points where stuff is happening on the map. Why do you reckon it is that your idea for non-uniform grids isn't making any ground?
When you change the grid, you then have to move your solution from your old grid to your new grid. And in doing so, you introduce more errors. And those errors can be so big that they will set off new thunderstorms. So it's certainly an area of research that, it's being used for, adaptive models like this are being used for tracking cyclones. If you know you've got a cyclone moving and you can move your grid to where the tropical cyclone occurs before it gets there, then it'll work. But for a global model, it's not clear that it's going to be beneficial. The other point is that a climate model is 1 million lines of code. And so for the Met Office or a similar forecasting centre to rewrite, it's a huge undertaking. And they need to be very certain that what comes out at the end is going to be useful. And the Met Office do rewrite. They're rewriting at the moment, and they're very carefully considering how they're going to do it.
Do you think that the future of climate models will hinge on radically new ways of constructing such models or on faster computers?
It won't be radical new ways of constructing the models. I think that there will be incremental changes. There have been incremental improvements to the climate models over the past few decades, and they will continue. And the computers will very slowly. The computing power is increasing much more slowly now. Moore's law, which means that computing power doubles every 18 months or something, really has stopped. So, in fact, improvements will slow, unless there's some fantastic new scientists and mathematicians to make them better.
If the models involve increasing the resolution of the grid sizes, and you have more computation to deal with computing more data for the grid sizes, do you have to have more recording stations to go with those grid sizes?
Well,
how does that work?
For a climate model, you're making a prediction 50 or 100 years into the future. So it doesn't matter quite so much what your initial conditions are. You're making an average prediction. For a weather forecast, your initial conditions are extremely important. But we've got satellites, and the resolution that satellites can measure the temperature and the winds in the atmosphere throughout the depth with higher resolution than the models can predict. So I don't think it's a limiting factor.
Earlier, if computational power currently is a hindrance, it's not sort of increasing as rapidly as you like, wouldn't it be better to look at radically new ways of actually modelling climate?
The Met Office say that they have one mathematician a week visit the Met Office and say they're doing it all wrong. What they want to do is rewrite their model like this, and it'll be so much more accurate. And they do listen, but they've got 1 million lines of code to rewrite. And so mathematicians are improving methods all the time. and the Met Office and other operation centres are listening. But it's not going to be, I can't see there'll be a revolution. We're solving the Navier-Stokes equations, which are the equations that I put up to predict the temperature and the winds. These equations have been around for hundreds of years, and people have been working on solving them. So I don't think there's going to be a massive change.
Recently, E equals mc squared was proven to be a fact until recently. There's this evidence that just come out, maybe that's not quite true. So you can never say never, can you?
Out of all the variables that go into your models, which are the least accurate?
The variables that go in. Deep ocean temperature. The deep ocean temperature is not well known. And there have recently been projects with Argo floats that float around the surface and then sink down to different depths, and when they come up, they send the temperature. If you want to make a decadal climate prediction, if you want to predict if the next 10 years are going to be particularly warm or cool, you really need to know the deep ocean temperature, and that's not well known for measurements.
Is quantum computing being used for climate modelling?
That's a terrific question. The meteorologists hate the idea of quantum computing because the meteorologists, they want to, if they try to run their simulation, if they put in a particular set of initial conditions, they want to get exactly the same answer every time. They want it to be bit reproducible. And because if you run a climate model for 100 years and then say you lose 10 years of data in between, you want to be able to rerun that 10 years in between, and you want it to do exactly what it did before and join up. However, even with current computers, because with the way that the atmosphere is divided over a number of different processes, it's really hard to write a model so that you'll get, as Culver described, it's really hard to write a model so that you can restart it. You have to write out all of your decimal places of your numbers and restart it and get exactly the same answer. And with quantum computing and GPUs and all sorts of new supercomputers, you'll never get the same answer twice, even if you run from exactly the same starting points. And meteorologists hate it, but it's inevitable that climate models will no longer be bit reproducible. They'll always give a different answer. It's a battle between mathematicians and meteorologists and computer scientists.
But isn't that actually one of the ways that meteorologists determine the reliability of their forecasts, by actually varying the conditions a bit and then running the forecast to see how much it differs?
Yes.
So, in fact, couldn't there be some value in these non-reproducible runs?
There is certainly. Meteorologists run ensembles. So if you want to make a forecast, so that, for example, the European Weather Centre, if they want to make a forecast for the next 10 days, they run it 50 times, each with slightly different initial conditions, so they can get a statistical answer of how the weather will change. However, if they did that statistical, that ensemble of 50 runs, and one of them produced a huge cyclone over the UK, which never happens. And then but they can't keep all the data. They throw it away as the forecast goes. And then it turned out that we did get a cyclone. You're thinking, we ignored that in the model. We thought it was a mistake with the model. We better go back and rerun it to see if we can do that again. And then you can't rerun it. But if you can't get the same thing again, it's incredibly frustrating. And you end up thinking, well, I did predict this, but I've thrown it away and I can't reproduce it again.
If these new mathematicians that are bringing through the new ideas aren't being accepted because it's too much to rewrite the entire code, how significant a change will have to be made before the code is rewritten? And if the change isn't made, will the code never be rewritten?
The Met Office rewrites their code about once every 10 or 20 years, which I think is very impressive. And at the moment, I'm working on a project with the Met Office. They are working out how to do the next rewrite. They're planning a project. They're going to rewrite everything. And so it's such a big change to go to a grid like one of these. And any new numerical method is on the table. The Met Office are considering it, and the mathematicians are working with the Met Office to try to plan in advance what they're going to do, which is difficult because the only way to know it's accurate, it's going to be good, is if you write the million lines of the climate model. So we've got to try and think up simple tests to try and work out what will be a good method. And so we have to rule some things out. For example, adaptive meshes, because we just can't consider everything. It seems to be too far off. But the Met Office do consider I'm really impressed by how much they do consider new methods, and they're constantly listening to mathematicians and going to conferences, listening hard. Thank you.